Right now in this video, I'm going to start to talk about trigonometric equations. A trigonometric equation is an equation that has a trig function in it somewhere, one or multiple trig functions. And the idea is we want to find the angles theta that solve the equation, that make the equation true. So for example, with this equation, tangent theta plus square root of 3 equals 0, what we want to do is find the angles theta that make this equation true. Make tangent theta plus square root of 3 equals 0. Now, unlike equations that you run across in algebra, trigonometric equations, if they have solutions, will have infinitely many solutions because trig functions are periodic. They repeat values. And therefore, there are two different ways that we can look for solutions. The first would be solutions in an interval. So we could ask for all the angles between, say, 0 and 2 pi that make this equation true. So we'd only list out a finite number of angles. The other thing we can do is find what we call the general solution, which will be sort of a formula that we can use to find any angle that satisfies the equation. And I'll show you both ways to go about doing this in this example. So to take a look at this problem, tangent theta plus square root of 3 equals 0. This is an example of a trig equation that is linear in form. We say that a trig equation is linear in form if it only has one trig function and that trig function is only raised to the first power. So here we just have a tangent theta. We don't have a tangent squared or a higher power of tangent, and there are no other trig functions occurring here. So for these sorts of trig functions, or trig equations rather, we want to solve them the same way we would solve a linear equation, like if this were x plus square root of 3 equals 0. That is, we want to isolate the trig function on one side. In this case, we just subtract square root of 3 from both sides, and we get the equation tangent of theta is negative square root of 3. Okay, so if that's the case, what do we know about theta? Well, tangent of theta is negative, which means we're going to be in either the second quadrant or the fourth quadrant. Since the tangent is negative square root of 3, our reference angle has to be pi over 3. Okay, which means we can be coterminal with 2 pi over 3. Okay, since 2 pi over 3 has a tangent of negative square root of 3. Or, in the fourth quadrant, 5 pi over 3. Okay, so that's what we know about our solutions. In order for tangent theta plus square root of 3 to be equal to 0, tan theta has to be negative square root of 3, which means theta has to be coterminal with either 2 pi over 3 or 5 pi over 3. Now, as I said, there are two different ways that we can look for solutions. The first would be to find the solutions in an interval. And usually the interval we use is from 0 to 2 pi. That is to say, all the angles greater than or equal to 0 and less than 2 pi that satisfy the equation. And in this case, our solutions would be theta equals 2 pi over 3 and 5 pi over 3. Since those are the two angles between 0 and 2 pi, which make this equation true. Okay, and generally, whenever I'm giving you problems on Canvas quizzes and exams, I will just ask for solutions between 0 and 2 pi, because That's a little less complicated. But the other thing we can look at is the general solution. Okay, that is, we can construct a formula to get any solution to this equation that we want. And here we would use the fact that our solutions have to be coterminal with 2 pi over 3 or 5 pi over 3. That is to say, if we start at the angle 2 pi over 3 and we make 180-degree or pi rotations clockwise or counterclockwise, we're going to end up at another solution. Okay, so notice that these two solutions lie in a straight line. If you start at 1 and you turn either clockwise or counterclockwise pi radians, you're going to get to another solution, and so on and so forth. So we can say that our general solution looks like theta equals 2 pi over 3 plus k times pi, where k is an integer. And Alex will write it like this, k in this kind of funny looking double struck z. So this just means k is an integer. Okay, so what this means is that if you put in any integer value for k, we're going to have something that looks like 2 pi over 3 plus an integer multiple of pi, which is going to be some number of half turns. And we can get all the solutions to this equation by starting at 2 pi over 3 and taking, continually many half turns. 1, 2, 3, 4, 5, etc. half turns counterclockwise, and 1, 2, 3, 4, 5, etc. half turns counterclockwise. That's going to get us to all the solutions, all the angles that are coterminal with 2 pi over 3 and 5 pi over 3. Okay, so this situation with the general solutions is a little bit more complicated, may take a little bit more getting used to, but this is the idea. Okay, so let's do another example. Okay, so now we'll look at the equation 5 cosecant of theta minus 3 equals 2. Okay, same sort of idea. This has a linear form because there's just one trig function, cosecant theta. It's raised to the first power. There's no cosecant squareds in there. We'll solve it the same way we would solve 5x minus 3 equals 2. That is, we'll isolate the trig function by itself on one side. We'll start by adding 3 to both sides, then dividing both sides by 5. The equation reduces to cosecant theta equals 1. Okay, so remember that cosecant is 1 over sine. Okay, so if cosecant theta equals 1, that's the same thing as saying sine theta equals 1. Okay, so if cosecant theta is equal to 1, or equivalently sine theta equals 1, that means that theta has to be coterminal with pi over 2. Okay, since the only angles that have a cosecant or equivalently a sine value of 1 are those that are coterminal with pi over 2. So then in this case, if we want the specific solutions between theta equals 0 and theta equals 2 pi, there's just one. That is theta equals pi over 2. That's the only solution we have between 0 and 2 pi. It's the only angle with a cosecant of 1 in that interval. On the other hand, if we want a general solution, okay, we can get an angle with a cosecant of 1 by starting at pi over 2 and adding an integer multiple of 2 pi. Okay, so if we take 2 pi times k, or 2k times pi is how Alex writes it, now we're going to have all of the angles that are coterminal to pi over 2, because these are all going to be the whole number multiples of 2 pi. So the idea being that we can write any angle coterminal with pi over 2 as pi over 2 plus an integer multiple of 2 pi, or 2k times pi. Okay. So let's do one last example here. And for this one, I'm going to change things up a little bit. For the first two examples, I had just theta inside the trig function. So the variable that we have, or the expression that's inside the trig function, is sometimes called the argument. So for both of the examples we've done so far, the argument was theta because we had a trig function of just theta. But we'll occasionally see examples where the argument is some multiple of theta, or some expression involving theta. Okay, so for example, if we wanted to do 2 times the cosine of 3 theta plus square root of 2 equals 0. Okay, so here's an example where the argument is 3 theta, but this is still a linear form trig equation because we have a cosine as the only trig function and it's raised to the first power. Okay, so we'll work through this the same way we worked through the other problems. And for the time being, we'll ignore the fact that we have a 3 theta instead of just a theta. We'll solve the problem the same way as we did the first two examples. So we'll isolate the cosine on one side. So we get cosine of 3 theta is negative square root of 2 over 2. And therefore, we'll think about what 3 theta needs to be. Well, 3 theta is an angle with a negative cosine, so that's going to put us in either the second or the third quadrant, since we have a negative cosine. Cosine is negative square root of 2 over 2, which means we have a reference angle of pi over 4. So in the second quadrant, we'd have to be coterminal with 3 pi over 4. In the third quadrant, we would be coterminal with 5 pi over 4. Okay, so we get that 3 theta is coterminal with 3 pi over 4 or 5 pi over 4. Okay, so for this sort of problem, it actually makes sense to get the general solution first, I think, then find specific solutions if we need them. I find that this is generally an easier way to go about things. So if we find the general solution, and again, we haven't solved for theta yet, so we're thinking about what does 3 theta need to be. 3 theta, again, has to be coterminal with 3 pi over 4 or 5 pi over 4, so that the cosine is negative square root of 2 over 2. If we're coterminal with 3 pi over 4, then we equal 3 pi over 4 plus 2k times pi. The other possibility is if we're coterminal with 5 pi over 4, we're equal to 5 pi over 4 plus 2k times pi. Again, k is an integer. In this situation, we have to write it as two separate possibilities because 3 pi over 4 and 5 pi over 4, they're a quarter turn off of each other, but if we start at 5 pi over 4 and we make a quarter turn counterclockwise, we arrive at something that's not a solution. So it's not like that first example where we had two angles that were pi radians off of each other and you could keep getting from one to the other by making half turns. In this case, a quarter turn will get us from this solution to this solution, but then a quarter turn would take us off of the solutions. So in this case, we have to separate this into coterminal with 3 pi over 4 and coterminal with 5 pi over 4. Okay, so now we can solve for theta by dividing both sides of our equations through by 3. So if we divide both sides through by 3, we get that theta is equal to, well, 3 pi over 4 divided by 3 is pi over 4. I'm going to do this maybe a little differently than how Alex does, but I like this a little bit better. So we have to divide both components of our equation by 3. So here we have to take 3 pi over 4, divide that by 3. That gives us pi over 4. Then we have to take the 2k times pi and divide that by 3 as well. Because again, we take both sides of this equation, take all the terms, and we divide by 3. So that would give us 2 pi over 3 times k. And then we have to do it with the second component as well. Okay, so this would be 5 pi over 4 divided by 3 is 5 pi over 12 plus 2 pi over 3 times k. Okay, so that would be our general solution. Okay, and then from there, if we wanted to construct our solutions between 0 and 2 pi, we would plug in increasingly large values of k. And here we have to do a little bit of arithmetic because we're adding fractions. The fractions have different denominators. So if we start with our first set of solutions here, so again, let's do the solutions between 0 and 2 pi. And from this first set, the pi over 4 plus 2 pi times 3 plus 2 pi over 3 times k, note first that pi over 4 is 3 pi over 12 and 2 pi over 3 is 8 pi over 12. Okay, so we'll need that moving forward. So theta is going to be, so again, I'm going to start with the first expression for theta. At k equals 0, we'd have pi over 4. Okay, so it would just be pi over 4 plus 2 pi over 3 times 0. At k equals 1, it would be pi over 4 plus 2 pi over 3. Okay, which is 3 pi over 12 plus 8 pi over 12 is 11 pi over 12. Okay, then if we add another 2 pi over 3, we're going to add another 8 pi over 12. This would be if k was 2, it would be pi over 4 plus 2 pi over 3 plus 2 pi over 3, or 11 pi over 12 plus 8 pi over 12. That's 19 pi over 12. And that's as far as we can go with that first set of solutions, because if we add another 2 pi over 3, if we add another 8 pi over 12, then we would have 27 pi over 12, which is bigger than 2 pi, because 2 pi is 24 pi over 12. So we get 3 solutions from our first term, and then we would look at our second term. So we'd have 5 pi over 12. Okay, that's if k is 0. If k was 1, we would have 5 pi over 12 plus 2 pi over 3. Okay, and that would be 5 pi over 12 plus 8 pi over 12 is 13 pi over 12. And then if we do it again, so we would have 13 pi over 12 plus 2 pi over 3. That would be 13 pi over 12 plus 8 pi over 12 is 21 pi over 12. Okay, and then again, we can't go any further, because if we add another 2 pi over 3, that's going to take us to 29 pi over 12, which is bigger than 2 pi, because 2 pi is 24 pi over 12. Okay, so if we take our, in this case, 6 answers and arrange them in order, usually we want to arrange them from smallest to largest. The smallest would be pi over 4. The next one would be 5 pi over 12. The next one would be 11 pi over 12. Then 13 pi over 12. Then 19 pi over 12. And then 21 pi over 12 we can actually reduce, because 12 is 4 times 3. 21 is 7 times 3. Okay, so that actually reduces to 7 pi over 4. And in this case, we get 6 different solutions: pi over 4, 5 pi over 12, 11 pi over 12, 13 pi over 12, 19 pi over 12, and 7 pi over 4 from smallest to largest.